Okay, this is going to be our fourth video on inductance. In this video, we're going to be covering all the material from section 30.4, and in this section, we're going to be talking about RL circuits. Okay, so we'll get right into it here. We're going to explore sort of how it works when we put an inductor into a circuit. Okay, so we talked about inductors before. Now we're going to look at them sitting in these networks, right? These circuits. We're going to use Kirchhoff's rules, specifically Kirchhoff's loop rule, to analyze these situations, and we're going to make use of our knowledge of inductors to also be able to understand how these things work in these networks. Okay. So we're going to find that the biggest difference between the circuits that contain inductors and those that don't is that in the case of circuits that do contain inductors, our voltages, currents, and the charges on our capacitors, if we were to talk about capacitors, although we're not going to talk about them in this section, they're all going to be functions of time. Okay, so they're all going to change in time. Usually when we have a circuit, we have some circuit elements in there, and as soon as we connect the circuit up, we have a current flowing, and then when let's say we have a switch and we turn the circuit off, we no longer have current flowing, right? And there's no sort of in between. It's either current flowing or it's not flowing. When it is flowing, it's flowing at the maximum, at the maximum value that the current is going to take from the moment we turn it on. This is no longer the case with inductors, right? We're going to see that the current is going to slowly build up. We're going to have current that slowly goes from no current, and it's going to asymptotically approach the final value of the current, and then it'll slowly drop back down as we disconnect our EMF here. But we're going to talk about all those sort of topics here in the next few pages, so let's kind of get on to that here. Okay, so current growth in RL circuits. So a circuit that contains both a resistor and an inductor, like we see here, our little drawing down here, and potentially some EMF source. These are called RL circuits. Okay, why RL? Well, it's called an RL circuit because we have a resistor. It's given the symbol R, and our inductor, we know that self-inductance is given the symbol L, and so these have become known as RL circuits. Okay, and so this R can either be sort of an external resistor that we've put into the network here, or we could consider this the internal resistance of our inductor, right? In reality, inductors are all going to have internal resistances unless they're made of superconductors, in which case there's going to be no internal resistance, right? But in general, you're going to be dealing with inductors that do have an internal resistance. So you can either have this resistance built into the inductor, or you can slap an additional resistor into the circuit and do calculations with that, right? So let's say we have the setup that we see here. We have an EMF source here. We have two switches, so the whole thing is shut off right now. There's no closed loop that we can make. But we have this setup, and then let's say that at some time, which we're going to call T naught, the time at which we start our stopwatch, we close S1, right? So we close S1, and what's going to happen? Well, what would happen if our inductor wasn't here? We would right away start having current going around this loop, right? We'd have current zipping around the loop here, and that current would go from 0 when the switch is open to whatever the current is going to be when it's closed, and it just stays that value for the whole time. With an inductor in there now, we know that the inductor sort of battles against or tries to slow down the change in current, right? So the current's going to take some time now to build up to its maximum value. So when we close the switch, at the moment that this thing closes, we're going to have no current flowing, and then it's going to slowly build up to some value which will be its final current, right? So let's start off taking a look at this loop here. So we know that the potential drops across AB and BC are going to be given by these expressions here. This is just a V equals IR from several chapters ago or from previous courses. And this is our new sort of expression for our potential drop across our inductor, right? So we have those two potential drops. We can now, and I kind of wanted to keep this on screen, but we can now apply Kirchhoff's loop rule to this, and if we go in a counterclockwise direction, we can imagine we're going in a counterclockwise direction from here. We go across our EMF source, going from low potential to high potential, and maybe I'll just do it with the equation in front of us. So we go up our EMF source, then we go across the resistor, going in the direction of the current, and we go across the inductor with the direction of the current, right? And so Kirchhoff's loop rule gives us this expression. We know this has to be equal to 0, right? Around the closed loop, our potential difference has to be 0. And so we can take this expression and we can solve. So this arrow here is just saying that this expression implies that we can solve for di dt. And if we do that, we end up with this expression here. And if we wanted to, we could separate out these two terms separately, right? Instead of having our EMF minus our current at that time times our resistance over our self-inductance, we can split these up into two terms, right? And why split them up into two terms? Well, we can kind of see what is going to be happening at different times more clearly if we look at it this way, right? So at the moment that we close S1, we know that our initial current, at that very first second, is going to be 0, right? This thing starts building up from 0 and then slowly asymptotically approaches whatever the current is going to be at some far distant time, right? So, but initially, when I is 0, our di dt here has to be equal to this value, but our I is 0, right? So this term just disappears, and we're left with our EMF over our self-inductance, okay? And so the greater that our L is, the slower our current is going to increase. Okay, that's just how inductors are going to work, and this is what we expect to see when we put an inductor in our network. Okay, but no matter how slowly the current increases, assuming that nothing else changes, we're going to slowly be approaching the maximum value that the current is going to take for this setup, right? So at some far off distant time, when the current, when our small I approaches large I, right? When our small I approaches the maximum value of the current, as though we had no inductor in there, our capital I here basically gives us the value of what our current would be if this L were simply cut out and we just had some conductor running across here, right? So the inductor just slows the pace at which our current gets there, but we still reach the same value. And we can kind of see that here because this is just a sort of rephrasing of V equals IR, right? This is just our EMF equals IR rearranged solving for the current. So our current ends up being what we would expect it to be, but it gets there more slowly, okay? And note, again, I mentioned here to note that I has no L dependence, right? Our final current has no L dependence. So we're approaching the value that we would have if there was no L involved at all, right? It's just that we're getting there more slowly, right? And we can kind of see a plot of how that looks here. So we'll take a look at it. We're going to talk about what some of these things are in a moment. But we can see that so we have time running across the horizontal here, and we have our instantaneous current running vertically here. So we see it at time equals 0, we have no current, right? And then we close the switch, and so we have some derivative of our, basically the slope here is going to be our di dt. This is what we found, this is what we talked about over here. So our di dt is going to be our EMF over L. That's the slope of this thing. And then slowly over time we're approaching asymptotically this current as though we had no L there, right? So let's say there was no L. What would this plot look like? Well, it would look like this. There'd be no current before we turn on the switch. We turn on the switch, current flows. That's it, right? But in this case, our inductor slows this process down, and we asymptotically approach the maximum current here. This is our current, our EMF over the resistance, right? We're going to talk about what tau here is in a second. So I won't mention it here, but sort of just remember where it's placed, and you can come back to this after we talk about it here in the next slide. Okay, so how do we generate this plot here? Clearly, this plot has to come from somewhere. The way we generate that plot is we take equation 3. So I'll just take a look at equation 3 here. This is our di dt is equal to the stuff that we learned from our Kirchhoff's loop rule going around the loop, right? So we can we can and we did solve for di dt here, and now we can rearrange that expression so that we have all the di's and the i's on one side and the dt's on the other side, and when it's arranged in this way, it's sort of just begging to be integrated, right? So when we see it like this, we can then integrate both sides. We're going to replace the I and the t with dummy variables, and we're going to integrate from 0 to I and from 0 to t. Okay, so if we do this integration that we see here, we do both those integrals, we end up with the expression that we see here. Okay, so this is great because we now have explicitly I solved for with no di's or dt's. We can solve for I in terms of the variables that we already know. Okay. So if you take this expression, you exponentiate both sides and you clean things up, you're going to end up with an expression for I that looks like this, okay? And this expression, this is the current in an RL circuit with an EMF as it's charging, okay? And maybe I could have done a better job about explaining this thing here, but as it's charging, okay? And so this is our expression as we're and maybe I shouldn't even say that it's as charging. Maybe I'll come back and I'll actually write a little bit of a better blurb for this here. But basically this is the expression that we have as we turn on the switch and we have current slowly starting to climb up to build up to its maximum value from 0. Okay, so that's our expression. If we take the derivative of this, di dt, we end up with di dt again. We are going to have the expression for the slope of this thing at every point, right? So now what we have, this di dt is giving us the value of the slope at every point here, okay? That's the expression that we have here in this box, okay? And if we take a look at this and we substitute in some values, we're going to find the behavior that we expect. So we know what we expect from di dt. We just talked about it sort of a minute ago, right? But what are we expecting? So we're expecting that as we just initially turn on the switch, as t is equal to 0, or just a tiny number, well this exponent here, this exponential value is basically going to go to 1, sorry, because the exponent's going to go to 0. And so we're going to end up with our EMF over L, which is exactly what we said we expected to find at t equals 0, right? And then as our time gets long, as we end up way farther out, and the time is getting very long over here, we're going to end up with basically a straight line across like this, straight horizontal line, which has zero slope to it, right? So we expect a di dt of 0 there. Is that what happens as we let t go to infinity in this setup? Well, yes. As t goes to infinity, this whole thing goes to 0 basically. Okay, so it's giving us the behavior that we're expecting. So that's good. And we kind of want to remember these two expressions. These are the key expressions to take away from this discussion. Okay. Also the meaning of what tau is here, which I'm going to talk about here in the next paragraph. Okay, so this quantity L over R, this is a measure of how quickly the current builds up to its final value in this circuit. Okay, so we give L over R the symbol tau, okay, and we call it the time constant for this circuit. So tau is equal to L over R. That's our time constant for the circuit, and it tells us sort of how quickly we're going to have our current going from 0 to its final maximum value. Okay. Yeah, so we're going to have an example coming up here. Before we do the example, I have one more note to make here. We can get some additional sort of insight into the behavior of these RL circuits by examining what happens with the energy as we flip the switch here, right? So let's take equation is it 2 or 3 from above here? Equation 2, when we've just done the Kirchhoff's loop rule. We're going to multiply through. Okay, we're going to multiply through by I, and if we do that, we end up with this expression that we have here. Okay, and if we look at these terms, each of these terms should sort of look like something. This term here, this term looks like power, right? And that's exactly what it is. This is the power delivered to the circuit by our source, by our battery or whatever our EMF source was, right? So that's the power delivered by the battery. This second term here, this is the power dissipated in the resistor. This is the instantaneous rate at which energy is dissipated by our resistor. Okay, and this third term here, this Li didt, this corresponds to the rate at which energy is stored in the inductor. Okay, so we have energy being supplied. Some of that energy gets dissipated by the resistor. Some of it gets stored in our inductor, right? And that's exactly what we expect here to see energy being conserved. We have energy being supplied and energy being dissipated and stored. So there's no unaccounted for energy, which is exactly what we need by energy conservation. Okay, this is sort of similar situation to what we talked about in chapter 26 when we talked about the charging and discharging of capacitors. Same idea sort of goes here with some slightly different expressions, right? But the ideas are still somewhat analogous, right? Okay, so let's take a look at an example here. We have a little more to do after we've done the example, but we'll start off with the example. So this is example 30.6 from the textbook. We are analyzing an RL circuit, and so here's the problem. We have a sensitive electronic device. It has a resistance of 175 ohms, and it's connected to an EMF source that has negligible internal resistance by a switch. The device is designed to operate with a 36 milliamp current. Okay, but to avoid damaging the device, the current can only go up at a sort of reduced rate. We don't want it going from 0 all the way up to 36 milliamps right away. It can only change at a rate of 4.9 milliamps in the first 58 microseconds. Okay, so when we turn this thing on, we need to have some sort of an inductor in there that's going to limit the speed or the rate at which we can have our current increasing. We need it to be limited to no more than 4.9 milliamps in the first 58 microseconds. Okay, so like I said, we're going to put an inductor in here. It's basically going to give us the setup that we saw up here. This setup here. We can imagine that it's basically this setup that we have here. And so we switch on our S1, right? So we have the current starting to build up. We want to answer a few questions about this. First question in part A, what is the required source? So we want to know what the EMF is going to be. In part B, we want to know what the inductance required for our inductor is going to be, so that we were able to hit these targets, so that we're able to hit this maximum sort of target for our increasing current, the maximum didt that we want to allow in those first few instants, right? And then we also want to know what is the time constant, what's our tau for this network. Okay, so let's get right to it. In part A, we are looking for the EMF, for what kind of EMF our source has to have. So for this, it's pretty simple. We can just use V equals IR, right? We just use V equals IR. This is basically just telling us that our EMF is equal to IR. We can then right away, just by substitution, solve for this. We know what the final current we're looking for is. We know what the resistance of our network is here. We can just solve for this, so it's just going to be 0.036. That's our 36 milliamps, right? And then we have a 175 ohm resistor. Do the calculation. You're going to find that the EMF that you need is 6.3 volts. Okay, so that's the EMF that we're looking for. Now the next question is what's the L that we need? What's the self-inductance we need in our inductor to guarantee that we don't get a different didt than the one that we want. Okay, well, we have really only one way to calculate we have an expression that gives us our current in terms of other things that we know. So that's really the place to start here. So just writing down the expression from above, I'm just rewriting this expression here. So expression number 9. It's basically this here, 1 minus e to the minus r over L t. Okay, so that's the expression there. And we now want to solve this expression for L. Okay, because what we want to solve for here is L. We know all the other values. We have to be a little careful about the t and the I that we choose. We're going to choose the I that we want after t has passed, right? So we're going to have our 58 microseconds, and we want our I to be at 4.9 milliamps at that time. So we're going to substitute in for both of those. Let's remember those are the values we want. We don't want to be putting in a different I here, like we don't want to put in our 36 milliamps at this point. We definitely want to make sure that at 58 microseconds we're only at 4.9 milliamps. So those will be the values we put in. But before we do that, we need to be able to solve this for L. So I'll go through a little bit of that here. The first thing we're going to do is we're going to multiply through by a minus R over our EMF, right? So we'll multiply through by a factor like this. Basically, we're multiplying through this expression here. So on the left-hand side, we're going to end up with a minus Ri over our EMF. Is going to be equal to minus 1 plus E to the minus R over L T, right? I have to be careful. I know I didn't leave much space here. Yeah, it'll probably work out. So when we have this expression, we can move the 1 to the other side, and we're going to then take the natural log of both sides, right? We want to pull down this exponent here, so we're going to take the natural log of both sides after we move the 1 over. So we're going to end up with, and I'm going to do these kind of side by side to save space, so sorry if it's a little bunched up, but you're going to end up with a ln 1 minus Ri over our EMF is going to be equal to minus R over L T, right? And we're only one step away here. We just need to solve for L. So if we want to solve for L, we're going to end up with an L equal to minus RT over ln 1 minus Ri over EMF. Okay? And again, remember, T and I need to correspond at the values that we want, right? So our I and our T are the ones that we talked about. Substituting in those values, we're going to end up with an L, which is going to be equal to, well, we need our resistance. That's, well, we still have a minus sign. That's 175 ohms. We need the time. This is 58 microseconds, so we have 58 times 10 to the minus 6 seconds. And then in the basement here, we have the ln of 1 minus, we have our resistance over I at that time, so it's going to be 4.9 times 10 to the minus 3 times 175 over our 6.3, right? That's the EMF that we found just before here. So we'll take the ln of all that and then put it in the basement of this calculation here. So if you plug all this into a calculator, you end up finding that you have an L equal to 0.069 henries. Okay, that's the answer we're looking for there. That's the self-inductance for the inductor that we're going to put in here. That's going to limit the increasing current such that it doesn't give us a different value than what we're looking for here, right? Okay. And like I said, I've left almost no space here, but luckily C is small. In C, we're only looking for our time constant, right? So we know that tau, which is our time constant for this circuit, is equal to L over R. Well, we just calculated L. We know what R is. R was 175. Do the calculation, you're going to end up finding that our time constant tau is equal to 3.9 times 10 to the minus 4 seconds. Okay, and tau really is a time, right? So now that we've done an example with tau and we've talked about it, I'm just going to go back up to the plot here, and you can see that we're actually going to do another example that involves tau, but at this time, at this L over R, this is just a sort of characteristic time that gives us some information about what this curve sort of behaves like. All these curves for these RL circuits are going to have the same shape, right? But they're going to have slightly different scales on the side, and tau gives us a feel for what that scale is. It tells us what L over R is. And so we can see that at the time L over R we have this value. If you were to take L over R and substitute it back into your expression for I, you would end up with this value here, and this is really this height here, right, as you can see from the plot. Okay, so that was the first example we want to look at. We've kind of looked at these things, this situation transferring energy into the inductor. Now we're going to talk about energy being transferred out of the inductor, right? So we're going to talk about what happens. Let's say, well, like the setup says here, let's say at some other time, after S1 has been closed for a long time, we've transferred as much energy as we're going to transfer into the inductor as we can. So S1 has been closed for a long time. At that moment, we restart our time to be time 0, and then we simultaneously open S1, so that it breaks the circuit up there, and we close S2. So now we end up with this, where initially this thing has as much energy stored in its magnetic field as it's going to have. Okay, what happens at that point? Well, what happens at that point is we can again evaluate the whole thing using Kirchhoff's loop rule and the information that we have above. If we follow the same steps that we followed above here in exactly the same way, I mean, there's going to be slight differences because now we're talking about the inductor supplying the energy to the circuit, but you're going to end up with an expression for the current, and I should have boxed this one, that looks like this, right? So this is the expression for the current as our inductor is really the thing that's supplying the energy to the circuit. Okay, so that's the expression you would end up if you followed through with the whole analysis again. Okay, and like I said, the reason that we have this current is that the energy necessary to drive this current is being provided by the energy stored in the magnetic field of our inductor. Okay, so that's sort of what we would end up with, and maybe it's worth taking another look at the at our plot here again. So we start off with the maximum current that we were going to have, right, and that's given this value I naught. That's the current at the beginning time where we restarted our stopwatch. That's the maximum current we're going to have, and now it's going to slowly die off as our inductor feeds energy back into the network. Okay, so our inductor feeds energy in, and slowly the current dies off at some very, very far off time in the future. It asymptotically approaches 0, and so it goes to 0 at infinity, right? Again, here our time constant plays a role. At a time t equals tau, or t equals L over R, we end up with this sort of an expression. This shape again is common for all of these inductors. It's just that the scale is going to change, and tau gives us a feel for what that scale is going to be, right? The value here is going to be I naught over E. Okay. So this is the decay of our current in our RL circuit. We'll take a look at a quick example here, and we'll wrap this video up. Okay. So this is example 30.7 from the text, and in this example we are talking about the energy in an RL circuit. Okay. So when the current in an RL circuit is decaying, what fraction of the original energy stored in the inductor has been dispersed after or dissipated after 2.3 time constants, right? So we're looking at, basically when we say 2.3 time constants, what this means is at a time 2.3 tau, what amount of energy has been, well how much energy is left in the inductor, or how much of it has been lost. Basically it's just two ways of saying the same thing, right? So how do we get at this? Well, we can start off, we have our expression for what the current is going to look like around this loop as this inductor pumps energy into the system. It's going to look like this, right? And the other thing that we need here is the expression for the potential energy stored in the magnetic field of our inductor. So we have this expression here from earlier work. Okay, That's our potential energy stored in our, well, in the magnetic field of our inductor. This is the current running through the loop as the inductor dumps energy back into the loop. Okay. What we're going to do here is just substitute in this expression into this expression. Okay, so we're going to end up with U is equal to 1/2 L, and now we have to square all this stuff. So we're going to end up with I naught squared, and then squaring our exponential here is just going to end up giving us e to the minus 2 r over L t. Okay. Now what we're going to do here is we're going to gather up all these variables here. This 1/2 L I naught squared. We're going to call that U naught. Okay. And U naught is the energy stored at a time t equals 0, right? Because if t equals 0, then this whole upstairs here is equal to 0, and if this is equal to 0, then e to the 0 is equal to 1, and so this is the energy stored at a time t equals 0, right? So we're just going to call that U naught. Okay, so U naught will be equal to 1/2 L I naught squared, and this is going to be the energy, or I guess I can write it, energy at t equals 0. Okay, so we want to know how much energy is left after if we set t equal 2.3 tau, right? But 2.3 tau by the definition of what our time constant is, that's 2.3 L over R, right? And so if we substitute in, well, let me first write this like this. So we have this expression, e to the minus t r over L t, right? And if we now substitute in our t value to be 2.3 tau, which is really 2.3 L over R, we can see that the L over R is going to cancel with the R over L, and we're just going to have 2 times 2.3, right? So this is going to end up giving us U, and I should say probably U at 2.3 tau is equal to what? Well, it's going to be equal to U naught e to the minus 2 times 2.3. This is just U naught e to the minus 4.6, right? Okay, so if you solve for what this is, you can get a numeric value for that. And I have some space here so I can write it. If you solve for that, you're going to end up finding that this is just equal to 0.010 U naught. Okay, and this is exactly what we're looking for. What fraction of our energy remains or has been dissipated at the time t equals 2.3 tau, right? And this is the answer here. So we have I guess you could write something like only 0.01 over 1 or 1% of the energy remains, right? So we only have 1% of the energy remaining still in the magnetic field of our inductor, right? So 99% of the energy at 2.3 tau has already been sent back into the circuit, and in this case, I guess, dissipated in our resistor. Okay, so that's that example, and that's going to wrap it up for this section. Okay, I'll see you guys soon.